Hey guys, Mr. Riz here to help you out with the first part of chapter 4. We're looking at polynomial functions. Big scary word, but it's actually not too bad. So kind of warm up here, what we're going to do is to look at these equations and figure if you guys can tell me something about A and B. Okay, so A is the number next to the x, and if you remember from linear equations, that tells us the slope. So if the slope is going up, A would be positive. Slope is going down here, A would be negative. All right, now with B is the y-intercept. The y-intercept is where it crosses the x-axis. If it crosses down to the bottom here, B would be negative. Over here, B would be positive. So this should have a positive A and a negative B. We should have the opposite, a negative A and a positive B. Yep. Another way to say that is A is greater than 0 and B is less than 0. All right, now if we look at these quadratics here, A determines the direction, whether the graph opens up or down determines whether it's positive or negative, and C is the y-intercept. Now B kind of determines the axis symmetry where it's at, but we can look at these here and see this is a happy face, so A should be positive. C is down here, the y-intercept, and C is negative. This one here is the opposite. A would be negative, and C should be positive. There you go. Okay, is there anything that we could tell? And I just kind of told you guys there from B. No, that really just kind of gives us the axis of symmetry. We could do a little bit of math here to figure out whether A or B is positive or negative, but it takes a little bit of time there. Okay, so our first lesson here in 4.1 is to look at a graph and analyze the power functions and to graph and analyze polynomial functions. So a power function is any function in the form of ax to the n power, where a is basically some number that's not 0, and a is also known as the leading coefficient. N is the degree. So n is a value of the exponent. The power function has to have a positive integer m to be considered a monomial function. Later on in the year, we'll talk about what if that is a negative. Okay, so if we look at that, we can actually determine some end behavior. We can do a bunch of examples to test this out. But if we see a positive degree that is even, so a positive a with an even n, our functions are going to be like this, where they start up high and end up high. So as we go to the left, it's positive infinity. The right, it's positive infinity. So it starts up high, ends up high. Now, if we have a positive leading coefficient and an odd degree, we're going to kind of do a little zigzag here. We're going to start down at the bottom and end down at the bottom. All right, now over here, if we switch it around, have a negative leading coefficient, it's going to completely flip the graph. So if we have a negative even, so we have a negative leading coefficient with an even degree, no matter what the graph was, we're going to be down at the bottom to start and down at the bottom to end. If we have a negative degree, a negative leading coefficient and odd, we're going to be up at the top to start and down at the bottom to end. Okay. So the key concept here is that odd degree monomials always at least have one real zero because it has to go across, start at the bottom, go into the top, or start at the top, go down to the bottom. It's going to cross the zero at least once. Even degree monomials may have any number of real degrees, or they might not have any real zeros. So what we're going to do here first is to look at this. Let's describe the end behavior with this leading coefficient of -2 and an odd degree, and then still state the domain and range. All right, since the leading coefficient is -2 and it's odd degree, we're going to start at the left up high and work over to the right down low. All right, this is a monomial function, so the degree is all real, or the domain is all real numbers, and the leading coefficient is negative, so it is also a range of all real numbers. Okay, try this one on your own. All right, since we have a negative leading coefficient and a or even degree, we're going to start down at the bottom and end at the bottom. The domain will be all real numbers, but the range would be all numbers less than or equal to 0. Okay, so let's do this with the story problem here. We can use a table. So for water to flow through a garden hose at a certain rate in gallons per minute, or GPM, it needs to have a specific pressure in pounds per square inch, or PSI. Through testing and measurement, a company that produces a garden home determines that the pressure P is given the flow rate F is defined that P of F is equal to 3/2 of F squared. So if we were to graph this function and state the domain and range. Okay, one thing to notice here is that the A is a positive number. Even though it's a fraction, it's still a positive number, and N is 2. So since we have an even positive degree, we're going to start at pi, end at pi. The domain is all real numbers, and then the range is anything greater than 0. So we should get values that look like such. If we plug it into a table, we can see they repeat. We can use Desmos to help us out with the table too. Just make sure you put y equals, use x, and we plug those numbers in. Okay. So that's kind of easy. That's the first key concept, is making sure we understand end behavior. The next thing we're going to be looking at is looking at a polynomial and talking about its form or expression. So a polynomial in one variable, meaning just all x's, pretty much is what you'll see, is an expression where it's in some form where we have a sub n times x to the n power plus a sub n minus 1 to n minus 1 power. Basically, we are going to have a power or expression where we can put a leading coefficient and an x to some degree all the way down until we don't have any more x's. Okay, these are going to be all real numbers. Now they could be zeros. The only thing that cannot be a zero is the a sub n. Okay, because these terms are written in order from greatest to least, this polynomial is called standard form. So if we start out with the highest power here, x to the fifth, x to the fourth, and we keep going down, that's in standard form. The degree of the polynomial is the n of the leading coefficient, a sub n. All right, so a polynomial function is continuous that can be described as a polynomial equation in one variable. Okay, so basically, if we have anything that is a polynomial that can be written in standard form, it is going to be continuous. We can name these. So we've talked about ones before. Constants are just like y equals 5, y equals 2. Linears are ones that's like y equals 2x plus 5, or y equals 3x, or y equals negative 2x minus 4, okay, where we have an x. When we talked about quadratics in the last chapter, those are the ones with the x squareds. Now, they could have just been like x squared plus 4. It could have been something like negative 3x squared plus 4x minus 1. Those are all x squareds. And then beyond that is cubics. Those are x cubes. Now, some vocab words, there are more that exist, like quartic or fourth degree, quintic or fifth. But beyond that, really, it doesn't matter what we call them. We just say they are a 7th degree polynomial or a 23 degree polynomial. We just name it by how many degrees they are. Now, that will tell us the minimum times the graph of the polynomial intersects the x-axis. Okay, so one thing is we can figure out actually how many roots or how many intersection points we could be just by the degree. Now, they might be real or imaginary or multiple, but they go through. So we're going to go through this one here and state the degree and the leading coefficients of each one of these polynomials. Okay, first one here, we look, this is in standard form. So the degree would be 4 and the leading coefficient is 2. All right, next one here, the degree is 3, it's x cubed, the leading coefficient is 7. Now this next one here, this is not a polynomial because we have x's and y's. So it's not a polynomial one variable, and so we can't really write it in or express it, find leading coefficient, things like that. This last one though is, and we can see it's the degree of 5, that's the biggest exponent we have, and the leading coefficient next to that would be 1. Okay, so if we think about this here, Jameson says that the leading coefficient of this is 4. Is he right or wrong? I would say he's wrong because actually the leading coefficient should match or correspond with the highest degree. The degree is 3, so the leading coefficient should be 2. All righty, next we're going to look at these here. We're going to state the degree and the leading coefficients. All right. Oh, okay, no, this one here. All right, answer the question. Sorry, you saw this. What is the degree and leading coefficient? So is the degree 3? Take a second, pause this video. Here we go. Now, you guys might have saw that. Yeah, this one is not a polynomial because we have this 6 over x. That is not a polynomial within one term. We can't have that in the denominator. Sorry. Okay, kind of got cut off here. Why don't we skip this here? Biggest thing, if I give you this a big equation here, here's the leading coefficient, there's the degree. I don't know why that got cut off. Okay. I guess all they want to do is plug it in, but sorry, I got caught off. And we can get a graph. Okay, I'm gonna go through until we get to okay. Here's the next thing we're gonna do is if we look at this graph here, could we determine the polynomial degree of the graph and whether it has an even or odd coefficient? So the one thing to notice this here is I always look to see how many direction this changes. Easy way to tell is the number of zeros. So the zeros are where it crosses the x-axis. It crosses at -2, +1, and 4. So we have three real zeros. It's easy to say this is a degree 3 polynomial. All right, if we look at this one here, we can see that it crosses at 1, 2, 3, 4. This one has 4 real zeros. Okay. Next, we want to look at this equation here and analyze the extrema. So this problem here, this graph, looks like more got cut off here. We can see that it crosses at the three values, and the extremas are the mins and the maximums. Okay. Oh, okay. Here's f of x. They give us the equation, and then g of x is shown here. All right. So if we were to graph f of x, we get this graph here. All right. It has some extrema here. It looks like it has a max that's around -2, 6, and a min that's at like 1/2, 1/2, -1/2. And if we look at the g of x, it has a max that's around here and a min that's around there. Now, this one has no absolute or min or max. Those are all relative, but we do actually have an absolute min on this graph. So which function has the greater relative maximum? We look at the C, which one has the higher. This one's up at 6. That one's up at 2.5. So definitely the first one. Now the other relative minimum, we can look to see how far it goes below. This one goes down to about -2.5. This one only goes down to about -1/2. So the g of x has the lower minimum. Okay, we can look at the key features, the x and y intercepts, and we can see that the zeros here are 3, 0, and 1, while our g of x is at -1, 0, +1, and 2. So there are more zeros on the g of x. And the intercepts, the x and y, and then we can look at the end behavior of the graph too. Okay, let's pause this video. Let's see if you guys can identify. This is a big thing. There's a lot covering there. Can you guys identify the graphs based off of these equations here? Okay, so easy way to tell without plugging these into Desmos is to look to see whether they are even or odd graphs. So we know that b is an odd function, d is an odd function because we look at the degrees. Okay, so these are going to be b or d. Now, the other thing to look at is how many changes of directions we have. If this is degree 5, it may change direction 5 times. So we go up, down, side, down, and up. So we got multiple changes of directions. More than 3 changes of direction. We go up to the side and up. That's only 3, so that's why B is number 2. So that means D will have to be number 5. Now, we can see 3 and 4 are the even functions, so we have to figure out which one's which. Now, 4 just goes down and then up. So that's only 2 changes of direction, while 3 goes down, up, 4 directions. We can figure out the minimum degree based off of the number of directions the graph goes in. And so that's how we could tell, figuring out which graphs are associated with this without even plugging them into Desmos. All right, guys, thank you for watching. I know that was a lot of information at the beginning, but remember here, we can use Desmos a lot to help us out. You guys have a great rest of your day, and thank you for watching.